So this is all one. Okay. Hello. Hello. Shall we get started? Is there anything to discuss? Assignment 2 is now starting. People are making progress. Some people are done. Okay. I wanted, for those of you that were not at the review session yesterday, I just wanted to make one slide with some basic hints about the assignment. So for those of you that haven't started the actual picture drawing part of the assignment, these may not make much sense. But I always like to make sure that students sort of know roughly where they should be going. So first of all is that there are two completely different ways to solve the assignment. So one of the ways uses a bunch of calls to prefix scan and sort, like we talked about in recitation. And you'll probably want to use a library called thrust, like in the same way that when you write C++ code, you use STL, vector, and things like that. If you write CUDA, there's very fast implementations of things like sort, prefix sum, in a library called thrust. So it's perfectly fine for you to use thrust for your assignment. If you go in a completely different direction, I gave you some code where you might be interested in the function shared memory exclusive scan, which is essentially a prefix sum, that I gave you. So you can look in the starter code for this. It's in the file exclusive scan. So you just include this file and you can use it. The other thing that students sometimes don't realize, even though we wrote it in the handout, is that we give you two useful functions. You may not use them, but you can use them. One computes whether or not a circle is in a box, and the other computes, well, both of them are whether or not the circle is in the box. One of them is conservative, meaning it may be in the box, and it's very cheap to compute. And the other really does tell you if the circle overlaps a box. So you don't have to work out that math. I just gave it to you. And you can use these functions. And they're in circleboxtest.CUDA. And the extension here is CUDA.inl for CUDA inline, because it's just a header file that you can include. So I just want to make sure there's some stuff given to you, because I want you to think about the algorithm design and parallelism, not how to compute whether or not a circle overlaps a box. That would be a good graphics class problem. Okay, so that's the only thing I wanted to say. And I guess, the other thing I wanted to say is that the way I expect you, or the way it should happen, is that you should implement the simplest thing you can possibly implement. And it will be slow, and that's okay. And it's going to be slow, and then you're going to run your code, and you need to figure out why it's slow. So a student asked yesterday in the recitation, said, hey, I ran my code and it's really slow, and it turned out that that solution wasn't creating enough parallelism to actually use the whole GPU. So you'll write code, you'll measure its performance, like you did in assignment 1. You're like, not linear scaling, let's figure out why. Oh, it's load imbalance. And then you'll modify your algorithm and get a little bit better. And then you'll measure your performance again, and you'll modify it again. So even though the final solution may be only 100 or 200 lines of code, it may be very short, you will probably write that code 3 or 4 different times to get to the good solution. So that's a little bit different than programming assignments in other classes where you know exactly what to do, but you have to write a lot of code to implement everything. Here it's a small problem, but it's unclear exactly how to solve it at the beginning. So that's how this will work. Any other questions about assignment 2? Okay, so that's due on Tuesday night, and if you get stuck, just make sure you ask questions on WeChat or. Okay, so what I want to talk about today is, now that we kind of know how memory works in a modern computer, we know a little bit about cache coherence, we know a little bit about memory consistency. Now it's kind of interesting to talk about how to use that memory to write thread-safe data structures. And what I mean by thread safe is that multiple threads can be modifying the data structure at the same time. And so we were going to use locks. And I'm going to talk a little bit about how to implement locks. And then we're going to talk about how to use the locks. And then we're going to talk about how to not even use the locks and still be correct. So this lecture, hopefully you're sitting by someone you like, because I'm going to be asking you to solve a lot of problems. So let's get started. And so here's the first example from the class. So this is a simple implementation of a lock, but it is absolutely incorrect. So I wrote it here not in C pseudocode, but in actually assembly. So let me read the assembly code to you. There's four instructions. So let's say that the lock is an integer, and that integer is 0 if the lock is unlocked. No thread has the lock. And the integer is 1 if some thread has the lock. And let's say that that integer is stored at this location in memory, at some address, addr. So the implementation of lock says the following. It says we're going to load that value into a register, load mem addr into register R0. We will compare the value of register 0 to the value 0. So we're going to compare. That's the CMP instruction. And if the result of the comparison is non-zero, meaning not equal to, if R0 not equals 0, we are going to branch back up to the top of the assembly code. So jump back to the top of the lock. So this is just assembly code to say, while R0 is not 0, load the value from memory into R0 and check again. And then if R0 is 0, we will store the value 1 back into the address. So that's saying, is the lock 0? Yeah, is the lock 0? If it's not 0, try again. If it is 0, write 1 to it, which means that this thread is taking the lock. And unlocking is pretty easy, just write 0 to the lock. So as a warm-up, as we get started, I'm going to ask you to figure a lot of things out in this lecture. This code is incorrect. So talk to your friend and make sure that both of you can see why it is incorrect. We'll do this for 1 minute. What is wrong? What's the bug in my code? This is basically equivalent to this assembly looks basically like this for this season. Oh, sorry. Okay, so what is wrong with this code? Does anybody see the problem? And the reason why I wrote it in assembly is to help show off the problem. So let's get started. I would like to talk with you a lot in this lecture. Okay, so what is wrong? Does anybody see a mistake? Yes. What is the mistake? There is a mistake here. Okay, got it. Correct. So the real problem here is that this sequence of instructions, or really the compare, the load and the compare, and the store are not atomic. So let's think about what can happen if this is supposed to be a lock, and a processor is just executing these instructions. So processor 0 loads the address. So R0 equals 0. And on another processor, the thread tries to take the lock, so it loads 0 as well. So now I have 2 copies of 0. Both processors compare their value, R0 to 0, and they say, oh, the lock is free. And now they say, well, if the lock is free, I will take the lock, so I will store the value 1 into the memory address. And now 2 processors, or 2 threads, think that they have the lock. And so the lock is not correct, right? Because the point of the lock was to make sure that only 1 thread had the lock at the same time. Okay. So this is not correct code. Now I'm going to give you a new instruction, a little bit fancier instruction. So I'm going to give you this instruction, and I'm going to call this instruction test and set. It does 2 things. Okay? So it will load, it's like a load, and then it loads the value of this memory address, or at this memory address, into R0. And if the value is 0, it will go ahead and set the value to 1. All in one step. We guarantee that's to be atomic. And whatever value was read is what's stored in R0. So it looks like this. It looks like R0 equals mem adder. If R0 equals 0, mem adder equals 1. That's what this instruction does. So at the end of the instruction, R0 equals the original value of mem adder. And at the end of the instruction, memory is unchanged if the original value was 0. Sorry, it's changed if the original value it was not 0. And if the original value was 0, memory is changed to 1. So everybody see what this does? Okay. So now, given this instruction, can you build a lock? Talk to your friends. So I want to see you build a correct lock out of this instruction. That was the old version. Okay, so everybody see it? What do you guys think? I meant to ask you guys yesterday. I didn't ask you yesterday. What do you think?
First, test and set memory address, R0 memory address.
So we test and set, okay, mem address, and then what?
If it's not 0, then jump to lock.
Correct. Very simple. It's just test and set. If the test failed, do it again. That's all it is. And of course, unlocking is still just one instruction of setting the value to 0. So if the value in R0 is 0, what does that mean? That means that the lock was unlocked when we ran the instruction. And it also means that memory is now 0, because that's what test and set does. So it means that all in one step, I went to memory, I read the value, I looked around and said, okay, without anybody else touching memory, that instruction updated, and then put the original value in the register. Good. So this is a correct lock if your CPU provides you one of these operations like test and set. Now, let's think about how this, now that you know how cache coherence works, let's think about what's going to happen given this lock implementation. So I drew 3 processors on this slide. Again, I've never seen a machine with 3 processors, but I ran out of room on the slide. And so let's assume that the test and set is a write. So if we're thinking about this as in terms of cache coherence, test and set is always a write. Regardless of whether or not it actually writes the value, the coherence protocol will treat test and set as a write instruction. Because we don't know if it's going to fail or succeed, so we'll just assume that it succeeds and we'll treat it as a write. So I have processor 1 here, runs test and set, because processor 1's trying to get the lock. So processor 1 shouts out, this is coherent. So what does processor 1 have to shout out to all the other processors? Remember the students here last time? So if a processor wants to write to an address, what does it have to do first? It needs to tell everybody, right? So it needs to say, I intend to write to this address. That is the bus read X. Now, let's say all the other processors say, okay, no problem. We have, and what do all the other processors have to do before processor 1 can proceed with the write? What is it?
Control invalid state.
They have to invalidate their copy of this value. Right? So right now, processor 1 has the address in cache in the M state. All the other processors do not have the data in cache because they've invalidated. The test and set instruction runs on that address and succeeds. That means now that processor 1 has the lock. Now, remember your implementation. Your implementation says, okay, if I'm trying to get the lock, I will run test and set, and if it fails, I will run it again. And I will run it again. And I will run it again. So while processor 1 has the lock, let's think about what the other processors are trying to do, because they're trying to get the lock. Right? So let's say that processor 1 gets the lock. Processor 2 has invalidated their line, like you said correctly. Now what happens when processor 2 tries to get the lock? Because remember it's saying test and set, test and set, test and set. So what happens next? If I had to draw on the board what instruction processor 1 does next, or what does processor 1 do? No, processor 2 do next. So what happens next? Processor 2 is trying to get the lock. Processor 2 does not have that address in its cache. So what is the first thing that it will do? How does it bring that address into its cache? Somebody maybe in the back of the room. I will not continue with the lecture until someone tells me. So processor 2 is trying to take the lock. Processor 2 is executing instructions, and that instruction, what it wants to execute is test and set, and if that fails, test and set again, test and set again. Test and set is a write. If a processor is issuing a write to an address that's not in its cache, what must that processor do in a coherent memory system? You've answered the question. I know you know that.
You must first shout out.
Okay, fine. Okay, yeah, correct. But I was saying that you know the answer. I didn't want to hear from you. Okay, so it does. It has to say, I intend to write to this memory address. That's absolutely correct. So if processor 2 intends to write to the memory address, what does processor 3 have to do, given that processor 3 does not have a line? Processor 3 does nothing. What does processor 1 have to do? Given that processor 1 has the line, and the line is dirty, because processor 1 updated the cache line. What does processor 1 have to do when processor 2 shouts out? What do you think? Processor 1 has a cache line. Processor 2 wants to write to the cache line. What does processor 1 have to do, given memory coherence?
Invalidate.
Correct. Processor 1 has to invalidate its cache line. Now, it also has to flush the data to memory so that the value is 1 in memory. But that's true. So processor 1 invalidates the cache line. Processor 2 attempts to update, attempts to run test and set, and that fails. So it jumps back to the same instruction. Let's say that processor 3 now wants to write. Processor 3 is also trying to get the lock. So it will now shout out, I would like to try and do my test and set, which will cause the invalidation here. So while the lock is being held, the cache line that holds the lock is actually moving back and forth between all the other processors that don't have the lock. See how that works? So it's kind of interesting. This processor took the lock. This processor is the processor that set the lock to 1. But the processor actually doesn't have the cache line anymore. All the processors looking for the lock actually have the cache line. And so even though this processor 1 has the lock, and we want it to be running as quickly as possible so it can release the lock, all the other processors are generating all this shouting at the same time. So how does the release of the lock occur now? So what does processor 1 have to do if it wants to release the lock? It needs to write 0. So if it wants to write 0, what does it have to do? It says, I intend to write, because it doesn't have the cache line. It'll issue the bus read X. One of these processors, whoever has it, will drop the line. We will update the cache line to 0. And then one of the other processors now, processor 2 or 3, is going to try a test and set. And now it's going to succeed. So on the previous slide, there are two things. There is what processor has the lock, and what processor has the cache line with the lock. Those are two different things. So in this example, if I do this, when does processor 1 have the lock? It has the lock for the entire time. When does processor 1 actually have the cache line? Only right then, and only right then. Exactly. Kind of interesting. And while this thread is in the processor has the lock, we would probably like it to run as fast as possible right here. Because if it gets done quickly, you can release the lock and let other people go. But it's unfortunate that while this processor is trying to do this really important work, the memory bus is really, really busy doing nothing. Essentially generating all this traffic that makes no sense, or doesn't help at all. So that's actually, our lock implementation is correct, but not necessarily efficient. Okay, and here's a graph of exactly this behavior. So this plot is plotting the number of processors. So my slide had 3. Now we have like 15. And this is a plot of how long it takes to actually execute the critical section. So we'll say the critical section is the time that you have in the lock, this part here. And so this was an interesting measurement that the more threads you have that are all saying, can I have the lock, can I have the lock, can I have the lock, and generating invalidate, 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 it actually slows down the thread in the lock. So this is the average amount of time in this critical section, which is kind of the opposite of what we want to have happen. Is all of this wasted, can I have it, nope, can I have it, can I have it, slows down your whole program. So I'm going to talk in a second about how we can make this better. But before that, I just want to say, even though we've been using test and set, the instruction that's available to you on any x86 processor is actually called compare and exchange. It's basically Intel's test and set. So compare and exchange takes two registers, a destination and a source, and it says, assuming that there's some register on x86, this is like, you just assume this is like R0 in my previous diagrams. But if this memory address equals this register, we're going to set a flag register to 1, and we're going to set this memory address to be that value. So it's basically your test and set. It's load the value at this address, compare against this register, and if the comparison succeeds, put this value in this address. So it's basically test and set. So it'd be interesting to see if you can build a lock out of the real x86 instruction as an exercise at home. Okay, so what do we want out of our locks? Well, we would like the lock to be really fast. Like we'd like to be able to acquire the lock very quickly. We would like there to not be a lot of memory coherence traffic that gets generated to acquire the lock. And there's some other properties. We'd like this to work with many cores. Currently, our implementation takes one integer to implement a lock. That's good. Maybe we might want it to be fair, because there's nothing about the lock that we've implemented that ensures that all threads have equal chains. So I'm going to change the lock implementation to this now. So this is exactly what you said. I'm going to start writing it in C code now because it's a little bit easier to read. And so my lock says, while I don't have the lock, while the lock is not free. So the outermost loop is while 1, while I don't have it. Wait for the lock to become free, and then run test and set. And if test and set succeeds, you have the lock. Quit. Else, start all over again. So this code might seem a little weird, right? Because we have two while loops. So can you think about, I want you to talk this over, is why did I do this? Why is this lock potentially more efficient than the lock I had before, which was just while 1, if test and set return? Before I did not have the red line of code. So now this red line of code, my claim, is that makes this lock more efficient if there are a lot of threads always trying to get it. So think about that for 1 second, for 1 minute. What did I do? I played a little trick. Okay. Let's see what we let's see if anybody can figure it out. So let's say I'll start here. So and it's okay to say I have no idea, but I want more people talking. So for example, so one question. What did I do? Do you see what I did here? Why did I put the red line of code?
Because it's no need to send us readings.
Uh-huh. So that's am I writing to the lock or reading to the lock? I'm just reading to the lock, exactly. So let's think about, now that you know how coherence works, let's think about what happens. And that's exactly right. So everything begins the same way as before. Is, let's say processor 1 has the lock. But now let's think about what processor 2 is doing. Processor 2 is going to read the lock, bus read, and while the lock still has the value 1, it's just going to keep reading the variable. It's going to read 1, read 1, read 1. So it's going to load the value in the shared state. Processor 3 is also going to load the value in the shared state because it's reading. So now all the processors that don't have the lock are not writing and writing again, but they're actually reading and reading and reading again. And we know that all these reads, well, these are just cache hits. Because after the first read, the processor has the line in the shared state. So they just keep reading 1, 1, 1, 1, 1. And now, when the lock gets unlocked by processor 1, what happens? So processor 1 issues bus read X to get it into the M state. All the processors in the S state do what? They have to invalidate the line. Processor 1 will write 0. And then you're going to see a whole bunch of bus reads. All the other processors are going to read the line again. All of them are going to say, oh gosh, it's 0 now. And then all of them are going to issue bus read X because they're going to try and run this. And only one of them will win. So now what's happening is that when the lock gets taken, there's just no traffic at all. Just hit, 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 hit. When the lock gets released, all of the threads do a bus read. They pass this check. And then all of the processors do a bus read X to try and get in to win this race. And only one of them will succeed. So there'll be O of N or O of P bus read X's. So it'll look like this. Bus read, all these hits. Bus read X, unlock, invalidate, 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 invalidate. And then all of these bus reads to read the value. Everybody goes, oh, it's 0. I'm gonna go take the lock. And then they all try and get the lock. So instead of there always being bus read X's, now there is only bus read X exactly when there is an unlock. So it's a little bit more efficient. So much less interconnect traffic, which is good. It's more scalable because all these processors are not generating this traffic. Still, my lock is still an integer. There's no reason it's fair. There's no guarantee you'll ever get the lock. It may have slightly higher latency because I have to do 2 tests. I have to do read and then write. I have to do 2 instructions rather than 1 to get the lock if it's not contained. So let me give you just one more example of how to implement a lock. So you know how like when you go to a store, sometimes if there's a long line, they say, please take a number. They say, take the number and then we'll call your number when ready. For example, we went to the restaurant. When we went to the Peking duck restaurant. We got a number and we waited for like 2 hours. And then after 2 hours, they called our number and we were like, okay, it's our turn. So that's a way to organize. Imagine that like instead the restaurant, whenever any table finished, the restaurant said, there is a table free, and everybody ran to try and get the table, and the first one that got the table won, and then everybody would have to go back and wait. And then a new table becomes free, and then everybody runs to try and get the table, and so on. So that's what the lock that we just implemented does. So you could take this idea and implement a slightly different lock that is very fair and does not have all of this rushing around. So here's a new lock, and now notice it has two integers. There's one integer which says, this is the next available number, next ticket. And then it says, this is the ticket, who should get the lock now? So lock says, give me the next number. And then you wait for my ticket to equal who's ready, now serving, like the ticket that's now available. So my next ticket is like the next number the restaurant will hand out. And now serving is the ticket that whose table is ready. So notice that lock is pretty easy. It's grab a ticket, grab a number, and notice that this is it needs to be an atomic increment. And while my ticket is not equal who the restaurant is waiting for, I just have to spare. So the nice thing now is that this is all reads. I never have to do a write to take the lock. I only do a write when I start waiting, and I never do another write again, because this is a read. Now, it requires this more advanced operation, atomic increment, which I haven't given you yet. I've only given you test and set. But if there was this more advanced operation in the computer, we can do this lock, which only requires reads to take the lock. And notice that unlock is just increment the number for the next person. So if I could probably do a whole lecture on different implementations of locks, but I'm not. I'm going to move on. But I gave you 3 examples here in this first part of class. A very simple lock, making it a little bit faster by instead of test and set doing test and then test and set. And then another lock which isn't about everybody racing for one value at all anymore. So those are just some ideas of how to implement some locks. Let's talk about a few other atomic operations. Like for example, I said atomic increment here. So atomic increment meant read the value, add 1 to it, and then write the value all atomically. And if you actually look in CUDA or many systems, for example, there's all of these atomic operations. So this is an operation that says read the value at this memory location, compare it to this value, and store the maximum of these 2 numbers back into that memory address. So atomic max. So if you look at the CUDA documentation, you have all of these available to you. You may not use any of them in your homework assignment, in your code, but they're all there. And I wanted to talk about one special one right here. This one is really general. Atomic CAS. So atomic CAS stands for atomic compare and swap. So this is very close. This is basically the test and set. So atomic compare and swap takes an address, an old value, which is called compare, a new value called val, and executes all of this code atomically. So it will take the value from memory, load it, compare it to the value compare. And if the value in memory equals compare, it will write the value into memory. So it's basically test and set, except test and set had hard-coded compare was 0 and val was 1. So it's a little bit more general test and set. I give you 2 integers. You compare the address in memory to the first one. If the comparison is the same, you write the second one to memory. And you always return the old value. So if you call atomic cas, if you call this function, how do you know if it's succeeded? It's an interesting question. So atomic cas always returns the old value. So how do you know, you meaning I'm a programmer, and I called compare and swap. how do I know if the value in memory got changed? Because the return value is always old. How do I know if the compare and swap succeeded? So if I wanted to do this, bool success, and I had how do I implement this function? How do I do it? Try it.
If all the equals compare.
Right.
Just
Return.
return.
Yeah. Return old equals compare and swap adder comp value. Right. So if you want to know if it succeeded, you just check. Is the value returned the value that I gave it as old? So you just basically duplicate the comparison. Because remember, this isn't code. This is like a machine instruction. This is a machine instruction. Okay. So given that, let's work at it. Can you build atomic min if I gave you compare and swap? So atomic min should be this, atomic min and we'll call it adder and x. So I want you to return the minimum of adder and x so it needs to look like that. Because I want you to compute the minimum of what is in adder and the argument x, and make sure that the minimum is stored in memory, atomically. And remember, if it's not atomic, you could have a problem. Because let's say the value in memory is 10, and you try and compare it to 5. Well, the minimum value is 3. But what if you load 10, that made no sense. Imagine you load 10, compare it to 5. You're like, oh, 5 is smaller, therefore we should write 5 to memory. But at the exact same time, some other thread is comparing with 3. The other thread loads 10, compares it with 3, writes 3 to memory. But then over here, remember, I've loaded 10, compared it to 5, and then I overwrite the 3. So, can you build atomic min if I gave you compare and swap? Try that really quickly. And don't look ahead on the next slide. It's more fun to try and do it. People that are looking ahead are cheating. Not fun. during the break, I'm going to put the answer up here so you can take a break and make sure you understand it. Okay? So everybody sees, so we can all see the answer here. But I think what's more important is how does it actually work? What's the main idea here? Why is this a valid atomic min? So I start by just sort of computing the min. I read the value from memory, and I compute the min in a normal way. And then I have the atomic compare and swap. So if the atomic compare and swap succeeds, which is if atomic cast equals old, what do I know? Why do I know it is atomic? Because if you look at this and this is not atomic. The only thing that's atomic is the comparison and the right here. So all of this code is not atomic. But I claim that this is equivalent to an atomic min. So what were you thinking when you came up with, when you understood the solution, or when you came up with the solution? How would you describe this to me intuitively? What am I using atomic compare and swap to do? Why don't, here, let's see, let's go somewhere else.
I think it is like.
What am I using it to do?
It's like I assign a memory to a register, and if it is not changed during the process, then I think it is true, and you can make it to.
That's right. I'm saying that, well, to be atomic, it means I need to read the value, compute the min, and write the results, all without anybody else making any changes. So what I'm doing is I'm making a note of what the value was when I started. And then I'm using atomic compare and swap to check to see if, while I was doing my work, any other thread came in and changed things. And I'm actually assuming that if the value hasn't changed, then nobody else modified anything. And therefore, if I go ahead and write, it's as if things were atomic, because I know nobody else has tried to call atomic min. That's the philosophy of how I designed this. I'm using atomic compare and swap to say, has anything changed since I got started? Because if anything has changed, all this work that I've done is now maybe not correct. So I need to throw it away and start over. I need to read the value from memory, recompute the min, and start over. So that's why I said, well, what about these other operations? Because it's kind of interesting that atomic increment, I could read the value, and while I'm adding +1, some other thread could actually add 30, and another thread could come in and subtract 30, and my compare and swap would succeed. So compare and swap doesn't guarantee that the memory has not been written to or read. It just guarantees that the value is the same. So that's a very subtle difference. That in the case of atomic min, it's okay, because the value only always gets smaller. In the case of atomic increment, if you were trying to compute the sum of some numbers, well, it's okay if somebody else added 10 and somebody else subtracted 10, because the sum's still the same. But there could be some situations where you're really trying to assume that nobody else has touched the memory. And compare and swap doesn't guarantee that. It only guarantees that the memory is still the same as it was when I got started with my operation. And that's going to come back soon. So just remember that. I have another slide here of implementing a lock with compare and swap. You can kind of look at that on your own time. And then I just wanted to point out that if you use C++, and you wrap any variable with atomic, the C++ compiler will guarantee that any operations on that variable are in fact atomic. So this is I equals I plus 1. So you get atomic behavior ensured by the compiler. So you can wrap any object in C++ with an atomic, and it will guarantee that operations on that atomic on that object are atomic. How it guarantees that is up to the compiler. For example, it might put a lock and an unlock for you around your code, or if it's something simple like this, it might use a machine instruction like atomic add. So C++ determines how to do it. In C++, compare exchange strong. This is very much like compare and swap. This says compare the value of I to old I using the equals operator, whatever the equals operator for this object is. And if they're equal, replace the object with foo. So C++ 11 has a lot of useful things in it to deal with atomic behavior on objects. Okay, so, man, we have a lot to do. Okay, so we have to move a little faster. So now that we've talked about implementing locks, now let's talk about actually using them to do more interesting things. Okay, so the most interesting thing we've done in this class so far is atomic bin. So what I want to do actually is now I want to start working with a linked list. So what I have on the board, take a minute to just look at it, it's just basic linked list code. There's nothing surprising here. Every node in the list has a value and a pointer to the next node. And here I have insert and delete. And it's a sorted linked list. So if you look at insert, I want to insert some new node with value val. I will ignore the edge cases and stuff like that, but let's just assume that previous points to the head of the list, current points to the next item, and we will just walk the list until the current pointer's value, while current value is greater than value, or sorry, if current value is greater than value, we'll stop, and the new node should go right there. So the list is sorted, so the values are really small. And as soon as we get to a node, as soon as current is bigger than what I want to insert, I insert the new thing right before current, and I make the new node's next pointer point to current. So wait until current value is greater than what I'm trying to insert, and then new node next equals current, and previous nodes next equals the new thing. So just linked list insertion. And then this is just linked list deletion, where please find the value in the linked list, and then just walk over the linked list until the current node's value equals value. And if you find it, we need to delete it. And remember, deletion from a linked list means we need to take the previous value and make it point to the next value. And that's basically it. Previous.next equals current next, and then we can delete current. So I'm going to assume that all of you have seen linked lists, and this code makes sense. Okay? Good. Okay, so now, think about two threads running this code at the same time. And let's think about two inserts into the linked list. You're trying to insert, your friend is trying to insert exactly the same time. Talk with your friend for a second. I want to know what can go wrong with this code if there are two threads trying to insert at the same time. Really quickly. So let's try it. So let's say that thread 1 wants to insert 6, and thread 2 wants to insert 7. So here's my list, has these numbers, and we want to insert 6. So 6 needs to go here. And to insert 6, what are we going to do? We're going to say this node's next pointer will point to 6, and 6 next pointer will point to 10. Correct? So that's what I'll do. So this is what I want to do. Now, imagine the other thread is also inserting 7. So inserting 7 would look like this. So both threads, previous pointer equals 5, and next pointer equals 10, or current pointer equals 10. So let's assume that thread 1 updates previous next before thread 2. So thread 1 will say node 5 should point to node 6, and node 6 should point to 10. But then imagine right after that, and remember thread 2 is sitting here with previous is still equal 5, and current still equals 10. So thread 2 is going to say, oh, well, I'm going to make previous next pointer point to my node, my new node, 7. And you're going to end up with a result that looks like this. 2 threads are inserting in the data structure at the same time. If we go back to the code, both threads are sitting here with current, which was node 10. Current's value is 10. Well, that's greater than 6 or 7. We're going to stop. And then we're really quickly going to say, my pointer, my new node is going to point to 10. And that 5 is going to point to my new node. So one of the threads is going to make 5 point to its node. And then the other thread is just going to completely overwrite that pointer and make 5 point to its node. So one of the insertions just got lost. My data structure will either look like 3, 5, 7, 10, or it will look like 3, 5, 6, 10, depending on which thread won the race. So I was supposed to insert 2 things, and I actually end up only inserting 1. My data structure is missing an element. So let me think about another case. Let's say that thread 1 is inserting 6, and thread 2 is trying to delete 10. So now, thread 1 is right here, says, okay, previous should point to my node 6, and 6 should point to this future node 10. But imagine right at the time where thread 1 is making this new node point to 10, 10 just got taken out of the linked list. So now, the new node 6 points to node 10, which is no longer in the linked list. And we've just lost the whole rest of the list. Big problem. Big problem. So imagine we wanted to use some locks. We want to put some locks in this code to make the program thread safe. We want it to be correct. And if you take the philosophy of this class, which is do the simplest thing first, and then we'll try and optimize it, and I go right back to this original code, try to figure out, and I'm going to give you a little bit more time, I'm going to give you a whole minute, where do you put the locks to make this code safe? Just the simplest possible solution that you can come up with in 1 minute. Okay, so take 1 minute to go do this. Okay. Where would you put the locks?
2 locks.
Okay, add 2 logs. Where would you lock?
Between the changed values.
Where? Can you help? Where would you?
Maybe while we want to insert some element
Okay.
and we will add 2 logs between 2 log. 1 log is at the previous and 2 log, and the second log and the second log is in the next node.
So you want to lock.
I want the logs between the changed values while we want to insert a node, and I will add a log. I will add as a log in the previous node of this new node, and add another log in the next node of the inserted.
Okay. Are you sure that's correct?
I think maybe it is correct because.
Okay. So I'm going to hold that answer, and we'll talk about whether it's correct soon. Was that the simplest answer?
Is that a simple one?
If I said that if you gave me a correct answer, I would give you $1,000. And if you gave me an incorrect answer, I would give you no money. Is that the simplest answer you would go with? That for sure is correct. So you can either go with that answer, which may or may not be correct, or maybe there's a simpler one.
I think it's the simplest one.
Simplest one. Does anybody have a simpler answer?
Add node at the beginning and
Sorry?
then download at the end.
Where?
Node at the beginning.
Yeah, the simpler answer is why not lock here, and unlock here, and lock here, and unlock here. Is it correct?
Yes.
Are you sure? $100 or $1,000. So let's say that I put an unlock here, and a lock here, and an unlock here, and a lock here. Am I done?
I'm not.
So your solution deadlocks. So yeah, but in spirit you are correct. Is we only have 1 bit lock, and the easiest way to make the system correct is to say that only 1 thread can be modifying the data structure at once. That would be the first thing that anybody would do, because maybe this application doesn't spend a lot of time inserting into the list. So as long as it's correct, it's fine. It doesn't need to be fast. So I just want to point out that the first thing that you should always do in this class is let's go with the simplest solution. This is a correct solution. It will work for any number of threads. Now what's good is that it's simple and correct. What's bad is that, as we know, it's not particularly efficient, because it means we lock the entire linked list, even if 1 thread might be inserting at the beginning, and another thread might be inserting at the end. Okay. So the obvious question I will ask you next is, can you do a little better? Right? And so you were beginning to hint at a solution which is going to lock only the nodes that are necessary. Correct. So let's talk about that solution. So the way to think about that solution, and a very fun example, is if you are doing gymnastics. Right? So if you were walking on the handlebars, I want you to think about every one of these bars as a node in the linked list. Right? Now, at any one time, this man always has his hand on one of the bars. And if he lets go of the bars, what will happen? He will fall. So if he ever has 0 hands on the bars, something has gone very wrong. Right? And the same idea is that if we ever have 0 locks as we are walking through the data structure, something has gone very wrong. Because if we have 0 locks, that's about as good as not taking any locks at all. We have no guarantees. So let's go look at how this might work. So one answer would be to say, I'm going to take a lock, and then I'm going to release it, and then I'm going to take the next lock. And then I'm going to release it, and I'm going to take the next lock. But that's like letting go of the bars. Because whenever you release a lock, you have no locks. So you have no reason, you have no way of knowing what other threads are doing. So instead, we're going to always make sure we have at least one lock. So to start, let's just say, just to have a starting point, I'm going to take the first 2 locks. So when I have 2 locks, I can release a previous one and move forward with the next one. And then I can release the next one and grab the next one. And so in this case, we're going to delete the node 11. So at this point, I've found 11, but I'm still holding 10. Okay? So what happens if I want to delete? Let's say I release the lock on 10, because the only thing I want to do is delete 11. Is that okay? But remember, 10, to delete 11, I need to modify 10's next pointer. I need to make 10's next pointer point here. So what if, as I'm deleting 11, some other thread comes in and wants to delete 10? Then I have a problem. So that's why I'm always holding on to the previous node. So the invariant is, if I'm trying to delete 11, and I have a lock on the node before 11, I know that nobody is deleting 10. Because if somebody was trying to delete 10, they would need the lock on it. So if you're trying to delete something, we want the lock, and we always want the previous lock as well. So at this point, that's previous and current. And let's say thread 1 deletes 10, wants to delete 10. Well, it'll come, and it's trying to delete 10, but it cannot delete 10 because it can't quite get that last lock yet. Right? So now let's just say we carry out the deletion of 11. Now we're done with the delete. We release the lock. The next thread gets the lock and can do its delete. Okay? So the real code here, so here's the code. There are a few edge cases in here that I'm not going to talk about. But there's one detail is that I put 2 locks. I have a per node lock, and I have a per list lock. So the invariant, when I'm walking through a deletion, is I always want to have a lock on the current node, and I want to have a lock on the previous node. And then I need to have the node I want to delete and the previous node I want to delete. And so if you look very carefully what's going on here, this list lock is like a dummy lock that's the prev of the first node in the list. So I'll let you stare at that a little bit. That's more of an implementation detail. But the most important thing is just right here, is that as we're walking through the list, notice that I have prev and current, and then I make current, prev equals current equals current next, and then I hold on to my old prev. So I unlock old prev, and then lock current, but I'm always holding on to prev. So I always have one lock here. So I go from 2 to 1, 2 to 1, 2 to 1. So my picture showed that when we're deleting a node, we should always hold the lock on the previous node as well as the current node. My picture did not have an insert example. So it's useful to think about why in insert do we also have to hold prev. It's actually kind of for the same reason. If I'm inserting into the list here, and I don't have the lock before me, another thread could delete this node, and what I'm inserting could get lost. Right? So it's actually the exact same reason. So in both of these cases, the answer is always you hold the lock on the node that you want, and the lock on the node before you. And that means that nobody can come up from behind you and mess up what you're trying to do. So the term you probably hear is fine-grained locking. So like you're taking locks on little pieces of the data set so that different threads can work in different parts of the data set at the same time. In contrast to our first solution, which was very coarse locking, which is I put a locker on the whole data set at once. But there are some costs to this. One of the costs is that it can be kind of tricky to figure, out this. If you miss a lock somewhere, you might have a big problem. And this is a linked list. This is probably a very easy example. Other costs are now we have, our node just got 33% bigger. It used to have a pointer and a value. Now it has a pointer, a value, and a lock. Another problem is that now we used to actually just have to dereference a pointer to lock the linked list. Now we take a lock every single time, every single node in the list. And from the beginning of the lecture, you can kind of remember these locks are pretty expensive. It's a lot of communication to take a lock. So this is, there can be some challenges with the with the fine-grained locking implementation. And I suspect that in this particular example, it might actually be slower to have fine-grained locking if you had a fairly short list. It might be easier just to do the global lock. So this is why I say always do the simplest thing first. Because maybe we would have come up with this complicated solution, and maybe it's not quite as fast as we would have hoped. Here's an exercise that we will not do in class, but you may see appear on your next homework, which is, can you do fine-grained locking for a binary tree insertion solution, which is a little bit trickier than a linked list, but not too much. So I want to finish the lecture now talking about, let's remove locks entirely and still be correct. It's kind of interesting. So an algorithm that blocks, so there's a term called a blocking algorithm. And a blocking algorithm is an algorithm where one thread can prevent all the other threads from making progress. And so a great example of a blocking algorithm is any algorithm that takes a lock. So if I take a lock, that means that no other threads can manipulate this node. Or if I had a lock around the whole list, no other threads can touch the list. And a blocking algorithm can kind of have some problems if we think about how modern computers work. Like imagine that a thread takes a lock, and then the thread is not run by the operating system for the next 5 minutes. Then all of your other threads can't get the lock for the next 5 minutes. This is a common problem if you're making web servers where you have thousands of threads and only a few cores. So one thread might take a lock, the OS will swap out the thread, and all the other threads are just sitting there spinning for the lock for the next 5 seconds. Another example would be what happens if a thread takes a lock and then crashes. It means that nobody else can make progress either. So there's some reasons why blocking algorithms may be undesirable. So a lock-free algorithm is an algorithm that can always make progress, regardless of the state of any other thread. So compare and swap, or atomic min that we implemented earlier, is actually a great example of a lock-free algorithm. I could have implemented atomic min with lock, unlock, and this is my atomic min using locks. But we use compare and swap. So if I use locks, imagine a thread takes the lock, and maybe it takes a page fault, or maybe it swaps out. So maybe for thousands of cycles it can't run for some reason. No other thread can get the lock and do its atomic min. But in our compare and swap implementation, if one thread takes too long when it's doing its work, Some other thread will just have come and updated the min value, and no problem at all. So do you see the difference from a blocking algorithm, like with locks, and an algorithm that's just always trying to succeed and never gets blocked? So I'm going to talk about some non-blocking algorithms on some more sophisticated data structures now. So here's like the simplest one. This is one that you almost certainly should know because I see it asked in Java interview questions all the time. So imagine you want to implement a queue with an array. Microsoft used to ask this question all the time. Not the parallel version, but the sequential version. It is, please implement a queue using an array. And so this kind of code should just be like, you should be able to write this on the board for your interview without thinking. And so I implemented a queue with a head pointer and a tail pointer. So I have an array. I don't have a picture of this one. So let's say I have an array. And I have a head and a tail. Right? So push changes the tail, adds to the end. And pop moves the head. So it's a queue. We want to pull data, we want to bring data off the head, and we want to push data onto the tail. So at the beginning, head and tail are here. And head is going to be, tail is going to be where we're going to put the next element. So if we want to add 10 to the queue, we put it wherever the tail is pointing to, and we update tail. If we want to add more, we add it, and we update tail. 6, update tail. So the queue is just, tail is just pointing to the end of the queue. And if we ever push, we just take the item that head is pointing to, return that, and increment that. So let's say that we pop 10, we move head here. We pop 8, we move head here. And at this point, I have a queue of size 1. Head is here, tail is there. And if I keep adding elements, 7, 8, 7, 10, tail will just wrap around all the way to here. So this is your standard how to implement a queue very efficiently. Just circle the head and tail just chase each other. Now, what I did here is I made it a parallel queue. And I'm assuming that there's one reader and one writer. Only one thread does the push, another thread does the pop. So it's kind of like a pipeline with 2 threads. So notice that there are no locks, ever. And this code is in fact correct. So it's kind of interesting here because if one thread calls push, that thread is only changing tail. If the other thread is only calling pop, that thread is only changing head. So since the 2 threads touch different data, I don't need locks. So this is a very simple thread-safe, but lock-free queue implementation that works exactly only if there's 2 threads. And one thread is doing all the pushing and one very popping. So it's a very simple data structure, only 2 threads, and the threads never have to wait or synchronize with each other because I've carefully crafted my data structure so that one thread only touches head and the other thread only touches tail. No locks. Pretty fun. When head equals tail, the queue is empty. Correct? Right? For example, if I pop the last element here, I would pop 6 and then make head equals tail. So this is another example of the queue being empty, right? Notice that if I add a bunch of elements, and so tail goes all the way back around, it's hard to determine if they equal each other, if head equals tail equals empty, or head equals tail equals full. So if you look in the code here, it actually says if tail equals head minus 1, quit, don't insert. So we actually never allow the tail to come back around to match the head. So the queue is full if tail is 1 before the head. So that's how this code is able to distinguish full from empty. I actually waste one spot in my array. And there's another version of this code, which I'm not going to put, which actually allows this to work for, this worked with a fixed size queue, fixed size array. And I have another example, which I'll let you just read offline, about how it works when the array can be of arbitrary size. And you can still do this lock-free even if the array grows to whatever size. So I'll skip this for now. Now this is the one I wanted to talk about. Here is a stack. And a stack may not be the best example for a parallel data structure, but this is it. So now think about what we did with atomic min. And I've basically done the exact same thing here with a stack. So note that node has so this is a stack where I'm pushing onto the front of a linked list and popping from the front of the linked list. So the stack has a pointer to the head, to the top of the stack. And if I want to push, well, I take the new node. The new node's next pointer points to the old top. And the top now points to the new node. And if I want to pop, I take the top of the stack and return that. And I make the top of the stack equal to the old top next. So there's just a very simple stack. Now this is my first try. I believe, or my claim, and I want you to tell me if it's true or false, is that this is a lock-free stack. So what does this do? So let's look at pop. Remember what the top of the stack was when we got started. So let's save that off to a variable. Old top is the top of the stack when the pop operation starts. Okay, well if the stack is empty, don't do anything, who cares? Now the new top should be the top of the stack's next pointer. So that's the new top. And then look at this, compare and swap. This says, if the top of the stack as it is now is the same as what I expected it to be, what it was when I first got started, then go ahead and write in this new value of top. So this is just like the atomic min example, right? It says that if the top of the stack has not changed, go ahead and I'll make my edit. Same thing. And the same thing is up there. If the top of the stack hasn't changed while I was trying to add something, go ahead and let me make my edit. So the main idea is that as long as no other thread has modified the stack, a thread can proceed with its modification. Just like if no other thread had changed the value of min, I can go ahead and proceed with my write. So this is looking pretty good. Now there's one problem with what I've done here. Does anybody see a problem? This is actually tricky. It may be hard to see what the problem is. So the claim is that if top is the same as what top used to be, no one has modified that stack in between when I got started making my edits and when I finished making my edits. And in fact, that claim is not exactly true. So let me show you an example. This is a common problem in block-free programs that use compare and swap. It's called the ABA problem. And the ABA problem, ABA stands for this example exactly. So let's say that we had a linked list. Now, the linked list, the stack, let's say we had a stack, and the stack has 3 elements in it, A, B, and C. Now, in this figure, think of A, B, and C as being the addresses of these nodes, not the value in the nodes, but these are the pointers. These are the actual addresses of them. So some thread begins its process. It says, let's pop A, because I want A. So old top is A. New top should be B, correct? If we do our job correctly. Now, let's say that before thread 0 is able to commit the new top, before it writes new top as the top of the stack, thread 1 comes in and begins its pop. And so its old top is A as well. Its new top is B as well. And then it completes its pop. So thread 1 actually won. Thread 1 removed A. Now, if thread 0 would have done its compare and swap, it will fail, right? Because at the top of the stack, it's supposed to be A, and it's no longer A. Right? So, but let's just say it hasn't gotten to that compare and swap yet. And thread 1 keeps running. Perfectly reasonable thing to do. And let's say thread 1 goes ahead and adds D to the list. Pushes D. And let's say that later on, thread 1 also adds in A. So this is C code, right? So it popped that node struct off. That node struct had address A. Maybe it stuck another value in there and pushed the same thing, the same pointer back onto the list. So now the list looks like this. And remember, these are addresses of nodes, not values of nodes. So now the stack has 4 elements. Thread 0 has popped a value. Thread 1 has popped a value, and then added 2 more values. Now let's say that thread 0 does its compare and swap. Thread 0 does its compare and swap, and it sees, well, the top of the stack is still A. Everything's fine. And it succeeds, and if it succeeds, what will the stack look like? So if thread 0 succeeds with its compare and swap, given old top A and new top B, what will the stack look like down here? What nodes will it have in it? Somebody tell me? It'll look like this, right? Because B's next pointer is C, and it just wrote B right in as the top of the stack. So we just lost all of these edits in between because we were using compare and swap to say if the pointer at the top of the stack is still the same, we assume that no other operations on the stack have occurred. But that's not actually true, because these other operations added a bunch to the stack and then put the same pointer back on the stack. So we actually tricked our algorithm. It's called the ABA problem because there was A and then there was B, and we popped A and then put A back on. That's why it's called the ABA problem. So there are a number of solutions to this. So one solution would be, let's invent something more sophisticated, like every time we pop, let's increment a counter. And then let's simultaneously increment the counter and change top using this funny double compare and swap. But maybe you can do 2 compare and swaps at once. That might be a way to fix the problem. So now we're looking for the stack to be the same value. Well, we're looking for basically the number to be the same number. Now now you're asking for instructions that are just very fancy. And I can't give you that, but what most processors have actually is a regular compare and swap that happens to be on 64 bits. So a common solution is to actually put the pop count and top right next to each other in memory. and you can use a 64-bit compare and swap to swap the two values at once. So anyways, I'll stop there. That's basically what I wanted to get through. The rest of my slides, there's a couple more slides that actually are talking about more advanced ways to eliminate the ABA problem if you're writing lock-free things. And this is actually pretty tricky. People write papers on how to eliminate the ABA problem in complicated data structures. And if you look at the website, the homepage, I have a bunch of cool readings if you want to learn along with them. One interesting thing though is that if I have compare and swap, my linked list insertion, I move away from taking a lock at every node. And all I need to do is just do a little compare and swap. So as I'm walking through the linked list, I don't have to take any locks. And then when I want to insert or delete something, I can use compare and swap and pay the cost only when I'm updating. And just in the last second is, there's some nice graphs that this paper made, and this paper's on the website, of looking at the performance of fine-grained locking versus a lock-free implementation. So since we talked about linked lists in class, let's look at the linked list implementation. So this is the performance as the number of threads goes up. So x-axis is more threads. And the baseline is, so let me see here. This line here is the lock-free version. This line here, this dotted line, is the fine-grained locking version. So the interesting thing to note is that, so first of all, like the time should be going down with more threads, because we have more threads, so we should be getting faster. And the fine-grained locking version kind of gets better with a small number of threads, and then as you add threads, the cost of taking all those locks gets too high, and the program slows down again. So this is an interesting, so the linked list is actually a really good example for a lock-free data structure. Because different parts of the data structure can be operated on in parallel, and that's pretty good. Things like queues and decks, where everybody has to touch the same part of the data structure. Like a stack is an example where everybody has to touch the head. So there's contention there anyways. So the lock-free approaches are not significantly better than the fine-grained locking approaches. But this is a really nice example of comparing lock-free to fine-grained locking. And this is the reason why in Java, almost all of the concurrent data structures, like lock-free hash table, lock-free set, lock-free linked list, are actually all implemented with lock-free implementations like we talked about. So if you look at the Java standard library, much of it is lock-free. So I'll stop there. And so that hopefully just gives you a little bit of experience in thinking about how to use these laws. And we will give you a lot more experience in homework 4. So homework 4 will be, I'll probably give you a fine-grained locking problem, and I'll tell you to insert the locks. So, okay? All right, so we're good. See ya.